Welcome, ladies and gentlemen, to Pre-Calculus Foundational Skills, week number 4 of my 4-week series for getting you prepared for pre-calculus. What we're going to cover in this live stream is we're going to talk about how to write the equation. We're going to talk about discontinuities, how to identify them. We're going to look into graphing piecewise functions. We're going to learn how to graphing transformations. And then also I'll tell you guys a little bit more about that masterclass, the invite, plus the bonus and all the little details you kind of need to know for that upcoming course launch. But before we get into that, let's get through the math because again, this workbook is the workbook that I have provided is, sometimes people remember some things, sometimes they don't. So that's why I want to make sure we're covering all the foundational math you guys need to know. So the first thing is kind of coming down to writing the equation. Now, in this case, you see we're writing the equation of a line as well as a circle, and just some fairly basic ideas that when we're given information, we want to make sure we can write the equation, right? An equation is going to be a representation of all the points that make up that graph. So when we have a line, remember there's kind of two important things we're looking for the line. We're looking for our, slope, and either a point, and particularly if you're looking for slope-intercept form, you're looking for the y-intercept. But in this case, we don't have a y-intercept, right? We just have a common point. So you still could use slope-intercept form, but what I'm going to do is I'm going to use the point-slope form because I didn't say how I want the equation, right? You could write an equation of a line in many different forms. Just like a quadratic, a parabola, you can write in standard form, vertex form. There's a lot of different forms that we can write the equation. So in this case, I have the slope and I have a point, which is basically a x-coordinate and a y-coordinate that lies on the line. So what I can use is the point-slope form. Okay, and to use the point-slope form, this x1, y1 basically represents any point that lies on the line, right? So since this equation goes through this line, I can represent these as x1, y1. And then m we're going to use as our slope. So now all I simply need to do is y1, that's going to be a -3. I'm going to use parentheses just to represent that that's what I'm plugging in. I don't know why I'm doing that. Just so you can kind of know where I am plugging in everything. So that's going to be a 3. And then x minus 1. Let's put those in parentheses. Okay, so now you can see that I plugged in a -3, which is the y-coordinate. I plugged in a +3 for the slope and a +1 for the x1. Now it just comes down to simplifying. Y minus a -1 is y plus 3 equals 3 times x minus 1. Now there's an equation of a line, but you could also, obviously when we're writing the equation, particularly when we're dealing with, functions, we like to have those equations solve for y. So we'll have y equals 3 times x minus 1 minus 3. And then if you want to simplify this to slope-intercept form, you can go ahead and distribute that. So that's a 3x minus 3 minus 3, y equals 3x minus 6. Okay, so just remember when we have this given information, we want to look into how can we apply it to the equation we're trying to obtain. So, and for instance, I probably didn't mention this, but remember like the slope of the line, y equals mx plus b, right? That's one way. You could also look at standard form, ax plus by equals c, like another way to write the equation. Now, when we're looking for the equation of a circle, in geometry class, we kind of talked about a little bit of some different representations here. And I think the easiest one that most students remember, x squared plus y squared equals r squared. That is going to represent the equation of a circle. And obviously we get into this fairly in depth throughout pre-calculus. However, not always is the center at 0, 0. So sometimes we need to take into consideration that the center can move off of the origin, and therefore we'd represent that as hk. Y minus k squared equals r squared. Okay, so in this case, we have our center, which is going to represent our h and our k. H is always with x, k is always the kind of the y coordinate of the center. So that is going to be your h, and that is going to be your k. And then this is going to be our r. So you can see here in this case, I have my h and I have my k, and then I have my r. So I'm just again going to plug them into the equation that we're looking for. So this is x minus a -4 squared plus y, let's put that in parentheses, y minus 2 quantity squared. Oh, let's just put, you don't really need to put that in parentheses because it's a +2, so it's still going to be the same, but still, just to be consistent. And then we'll have 3 squared. All right, so x minus -4 is x plus 4 quantity squared. and then this becomes a plus y minus 2 quantity squared, and then 3 squared is going to be 9. Okay? All right, the next thing, discontinuity. So we've already kind of covered looking into, simplifying rational expressions, but now we're just going to talk about discontinuities. Like if we're looking at, graphing them, and the main discontinuities we're going to talk about is a whole, asymptote, as well as a jump discontinuity. So remember, a discontinuity is going to be a break in the graph. It doesn't mean that where the discontinuity occurs is there always going to be a break in the domain, because a graph can still be disconnected but have a domain of all real numbers. So I'm not going to get into the graphing portion of these, but just to kind of remind you of when a function is going to be discontinuous. So we'll kind of talk about that. So in this first part, we see whenever we see a rational expression and we want to find discontinuities or graph it or simplify it, just look into factoring, right? Look into saying, all right, can I factor this numerator? What two numbers multiply to give me -6, add to give me +5? Well, I know 3 and 2 work, right? And they add to give you 5, but you can't do a 3 and a 2 that one would have to be positive, one would have to be negative, and that's never going to give you 5. So therefore, it'd have to be a +6 and -1 would work there. So x plus 6 times x minus 1. And again, 6 times -1 is -6. 6x plus 5x, or I'm sorry, 6x plus a negative x would give you +5x. And then in the denominator here, this one's not as nice, right? We have this 2 here, but again, we know that it can be factored like this. All right. And again, like my main thinking is if it's going to simplify, which it doesn't always have to be, but if it is, then that means that it either needs to be a x plus 6 over here or an x minus 1. And let's just assume that they want us to do x minus 1. Like, does that make sense? Well, if that's -1 and I need to get to be a +1, that means that would have to be a +1. And does that work? 2x times x is 2x squared. 1 times -1 is -1. That's going to give us a positive x. That's going to give us a -2x. Well, x plus -2x is a -x. So you can see how that one actually works. So now the nice thing here is those divide out, right? Using the quotient rule, the division rule, division property. These expressions are separated by multiplication, and they're exactly the same. So they're going to divide out. Now, if we look into our last kind of training video, remember, like a function is going to have a discontinuity for any value that is going to make our denominator equal to 0. Like we cannot divide by 0. So even before I go ahead and simplify that, like I recognize this simplifies out, but still I recognize that there are going to be two different discontinuities. 2x plus 1 is equal to 0 and x minus 1 is equal to 0. Now again, I solve these both and subtract the 1, divide by 2, x equals -1/2. And x equals 1. So you can see for these two values, the denominator is going to be 0. All right. Therefore, these are not going to be in the domain. So they are going to be a discontinuity of the graph. Now, the difference is x minus 1 gets removed. It can be divided out. So that is what we call a removable discontinuity. And we can further label that as a whole. The next example is going to be the next example cannot be divided out, right? As I go ahead and simplify this equation, I'm just going to be left with an x plus 6 over 2x plus 1, okay? And now I can't like simplify this any further. So since this is non-removable, it does not get divided out. This is what we call a asymptote. Okay, so we have an asymptote, which is a non-removable discontinuity. And then we have this whole, which is what we call a removable discontinuity. And obviously in precalculus, we'll practice again graphing these and so on and so forth. But I just wanted to, kind of go through this understanding and this idea of when a function is undefined and what that means for the graph. Now, the next one, we have a little piecewise function. And remember, piecewise functions, again, is just going to be a combination of two or more functions. So that's really all we're looking into doing is just combining these two. So one function is only true for x values that are greater than 0, and the other function is only true for x values that are less than 0. Well, let's just go and look at what these two graphs look like separately. If I was just going to graph 5, 1, 2, 3, 4, 5, that'd just be a nice little line. If I was going to graph x squared minus 1, then that would just look like this. Okay? So obviously we can't graph both of them because then they wouldn't pass the vertical line test. So what we need to do in this case is we only need to graph them based on their restrictions. All right, so let's go ahead and practice here. So if I'm going to graph 5, it says only graph 5 when x values is less than or equal to 0. So that when x is 0, right to here, we're going to graph or less than 0. So that's going to be to the left of the y-axis. We're going to graph this graph, which is 5. So that's going to look like this. 1, 2, 3, 4, 5, right? You're going to do a closed circle because it is included. And we're just going to go to the left. Nice little horizontal line. So it's basically this whole graph, but only for x values that are at 0 and then less than 0. And then for this graph, x squared minus 1, that's only going to be true. We're only going to graph that function for x values that are greater than 0. So again, at 0, but greater, and not including 0, right? So we're going to use that as going to be an open circle. And again, I'm not trying to be perfect here with that. But here you can see that now what we have is what we call a jump discontinuity. All right, so you can see that basically we're going from one graph and we have to jump, if you're like a video game, you'd basically have to jump from one graph to the next. So that is something that is kind of special about those piecewise functions. Not always do they produce jump discontinuities, but that is something to look out for. They also produce asymptotes and holes and all that kind of stuff, but that's one thing that they are going to be kind of special with as far as looking for that jump discontinuity. And again, I showed the graph to kind of represent that. Another way you can kind of see if what the discontinuity be would just be to plug in 0. And that's what we kind of talked about last training as far as like continuity. On the left side, you can't plug 0 into anything. It's just 5. So that's going to stay the same. However, on the right-hand side, if it's x is greater than 0, we're still going to plug in 0. And you can see that 5 does not equal -1, right? At 0, we have 5 and we have -1. Well, those aren't the same. So obviously you can see there is a discontinuity. So therefore, something's happening. But I think understanding what the graph would look like is going to be your best bet as far as understanding the type of discontinuity. All right, on to the next one, which is graphing transformations. So this one gets students a lot because we have to go and remember, like basically from Algebra 2, we talked about a lot of these transformations, and we've focused a lot with quadratics and maybe absolute values. But the cool thing about this is they expand to any type of function that you're dealing with. So it's really, really going to be helpful, especially when we start getting into more advanced transformations and more advanced functions, that we understand what is happening to the function. So I am going to work with just 6 functions that we should be familiar with coming into pre-calculus. Maybe you don't remember what the graph looks like, but again, you can just quickly go on to Desmos, and same thing, graph these. And also over here, graph these, see what these graphs look like. Just remember that Desmos is not going to show you an asymptote or a hole. So that's why it's important to understand what the discontinuities are. All right, so on the first one is I will graph them just because I want you to remember what these graphs look like. And I know a lot of students do not remember the graphs. So hopefully you can just kind of follow along with at least what the transformation is and then what the graph is. And actually, you know what I'll do? I'll graph the original, the parent graph, as well as the graph with the transformations. So the parent graph in this case is just going to be x squared. So that's going to look like this. And again, I'm just going to do a horrible graph. Okay. If you multiply by negative on the outside, all that's simply going to do is that's going to reflect it across the x-axis. The square root of x, that is going to be your parent function. Now you can see that we're multiplying by negative inside of the function. So the parent graph, looks like this. If I'm going to now reflect it or multiply by negative inside of the function, you can see that's under the radical, so it's inside the function. That is now going to reflect the graph about the y-axis. Okay. The next graph is the absolute value graph, a lot of times what we call the V-shaped graph. And again, that just looks like a V. Now you can see that we are adding a 2 inside of the function, right? So we're not multiplying like by negative. Now we're just adding 2. Well, what that's going to do is that's going to shift the graph 2 units to the left. Everybody wants to think it's 2 units to the right. But again, if you look at Desmos and you look at like graphing that, you can see how it actually shifts it 2 units to the left. And that was something we kind of talked about too, looking in those trainings. Or yeah, actually I was thinking of the course videos that I was making. Actually, I just went over some of that. All All right, for the next one, we are now subtracting a 3 outside of the function. So you can see how, like, if this was inside of the function, it would be inside of like the under being raised to the third power. Since I'm like we're adding 2 is inside of these, inside of the absolute value sign. The negative is under the square root, right? But here you can see this is outside of the function because our traditional function here is x cubed, right? So if I'm keeping x cubed the same, then whatever my operation is outside. See how x squared is still the same? It's just being multiplied by negative. But do you see how square root of x is no longer the same? It's square root of negative x. All right, so this is going to be an outside function you're subtracting, and what that's going to do is that's actually going to shift the graph down 3 units. Now, the cube root function is what we call the S-curve graph, and that kind of looks something like that. So if I'm just to take that graph, I'm going to shift it 3 units down. It's going to look something like this. And again, I'm not being perfect here, but good to go. I wanted to include this one because I know a lot of students are not going to remember the reciprocal function. So that is just one kind of that is, I think, helpful to kind of cover. But just remember this function has 2 asymptotes. So this is what we call it's a reciprocal function. So just remember that there is a horizontal asymptote and a vertical asymptote. All right, and this graph is going to look something like that. Now, if that's what the function looks like, what is this 2 going to be doing? So a lot of times with this, it's going to be helpful to rewrite this problem. And what you can do is you can factor out the 2 in front to write this as 2 times 1 over x plus 1, okay? So 2 times 1 over x plus 1. And so what is this 2 being? Well, again, is the 2 inside or outside? Well, since my 1 over x is pure, right? It didn't change. That 2 is being outside. So if I'm multiplying something on the outside, what is that going to do? Well, it's not negative. It's not reflecting, right? You're not adding or subtracting, so it's not shifting. So when you multiply by 2 on the outside, that is actually going to be a vertical stretch. So I know this might look a little weird, and it is kind of hard to like graph a vertical stretch with the reciprocal function. So I'll just kind of do something like that. Oops, I'm sorry. And then also, now we're adding a 1 outside the function, so the graph is being shifted up 1. Now, the reason why I wanted to bring this up is because if you shift the graph up 1, not only does the graph move up 1, but so does the asymptote. Okay, so that was kind of the important thing to bring there. That's a horrible graph, but hopefully you guys can make some sense out of that one. Sorry, it's a tough one to be. All right, and then the last one is, again, another quadratic. So you can see that this one looks pretty kind of confusing. Like you have an x squared. Now, a lot of students might say, oh, you're multiplying by 2 again. So that's going to be a vertical stretch. And you're adding 1. So that's shifting to the left one. And that's why I brought in this problem, because you have to be very, very careful. First, see how this 2 is outside the 1 over x? Here, the 2 is inside, right? It's being inside the parentheses of what is being squared. So one thing you want to remember is that is not the same. Multiplying outside is not the same as multiplying on the inside. Now, we'll talk about that in just a second. But the other thing we need to understand is we're actually not adding this to, we're actually not shifting it 1 to the left either. What we need to do in this case is actually factor out that 2. Okay, because again, that's the same thing. If you multiply the 2 back, 2 times x is 2x, 2 times 1/2 is 1, okay? But now we can see, oh, now my x has a coefficient of 1. It's being multiplied by 2, and actually you're shifting it 1/2 to the left, not 1. So again, we'll just have our standard parent graph. Okay, but if I'm going to, since I'm multiplying by 2 on the inside, it's not going to be a vertical stretch. It's actually going to be a horizontal compression. So it's going to look very similar to a vertical stretch, but it's not going to be the same. All right, so it's going to just be a little bit skinnier. All right, and then, oops, what am I doing? It's going to be a little bit skinnier, and then also it's only going to be shifted 1/2 to the left. Okay. And that's basically our transformations. I think walking into pre-calculus, you should be at least somewhat familiar with the basic transformations as well as these graphs, because all we're going to do in pre-calculus is just expand upon the graphs as well as the transformations. And then the other function that always gets students, so confused is the understanding with the piecewise functions. So again, let's just go ahead and cover here for piecewise functions that you didn't need to graph it to understand the discontinuities, but I think it's always helpful to have a big picture idea of how to graph a piecewise function. And again, what we've talked about in this training and in previous trainings is it's all a piecewise function is a combination of two or more functions. So in this case, again, we have this zero restriction, right? Here's when x is equal to 0. So anything to the right or equal to 0 is going to be this graph. Anything to the left of 0, right, is going to be that graph. So you could graph them together on the same graph and then apply the restrictions. Or if you have something like this, you can say, all right, well, I can graph this line, right? This has a y-intercept of -1 and a slope of 1/1, right? So I'm going to go down to -1. Now it's greater than or equal to, so I know at least that equal to it's going to be a solid point. And now you just follow the slope. Well, slope is positive 1/1, so up 1, over 1. And then I have 2 points, so I'll just go ahead and sketch my graph there. Now, on the next example, it says x is less than 0. So again, it's not less than or equal to, so it's less than. That means I need to go ahead and use an open circle. I recognize that I have a different y-intercept, so that's going to be at +2. And then my slope is going to be negative. Now, we could go like down to the right one, but again, like that's going to be for positive x values. The restriction on my graph is for only x values that are less than 0. So therefore, instead of going down and to the right, I'm going to go up to and to the left. And there'd be that graph. And that is graphing a piecewise function. You can see that, again, we have another jump discontinuity. For the next graph is you can see that we have again, another like number and an equation, but this one's a little bit different. This one says graph x minus 1 squared for basically all values, but just don't graph it for when x equals 1. And then graph number 3 only for when x equals 1. So basically that's another way of saying that's going to be a dot. So graph the function 3, but only when x equals 1. Well, when x equals 1, y equals 3. So basically that is just telling you to plot the point 1, 3. All right, so if we go and look to graph this. So x minus 1, hopefully in the last section, you recognize that this is going to be shifting it 1 unit to the right. So whenever we're adding, notice how this is a 1 inside of the function. And since it is... you're adding or subtracting, right? That's going to be a shifting of the graph. And when we add, we go to the left. When we are subtracting, we're going to be shifting it to the right. However, if we have our vertex, right, would be at 0, 0. When we shift it to the right, my vertex is going to be at 1, 0. Well, x cannot equal 1. So what do? We're just going to use a hole. All right. So we're going to have our graph is going to look something like this. But again, x cannot equal 1, 0. Now, what can we do at the point 1, 3? Well, we can go over 1, up 3. And here what you guys can see is it is a graph with a hole, right? Which is going to be your discontinuity. It has a hole, but it has a defined value. And that's kind of interesting because what that means is the domain is going to be all real numbers. Actually, both of these, they both have discontinuities. They're not continuous graphs, but their domains are defined for all real numbers because even though it's undefined here, it's defined there. Even though it's undefined here, it's defined there. So just remember, you can always separate piecewise functions by graphing them separately and then combining them based on their restrictions. But I think the more and more practice that you get, understanding the restrictions, understanding what type of discontinuities you have, you can start just graphing them on the same graph or the same piecewise function and going from there.